Good morning, all. So we are in this class we will study about steady state errors. Okay. So the contents are as follows. We'll give a detailed introduction. Okay. I'll give you some example. My friend Mr. Anfas, who was helping me in making the animations, suggested that introduction examples could be in the beginning. Okay. So I will spend some time on that, and I have often found that students enjoy examples and stories, and so the other things you will get on your own. Okay, so this is, I hope you will be motivated to learn the remaining portion, and you will learn why we learn all these things, or you will realize why we learn all these things by looking at the examples. Then these are all very routine stuff, and I will do very slowly because concept is important, examinations are also important. So these portions is easy. So I debated with myself whether I should give an detailed video, and you could study this on your own. That is the best part. Then I thought maybe some students would benefit by watching the video. So I thought I will do this very slowly because this is like if you listen to my video, I'm sure that with God willing, you will be able to get 5 to 10 marks for your university examination. So this is very easy topic. Okay. So even though it is easy, I will go slow because I want all of you to be comfortable with this topic. So type number is something like very important for this. I will say about that. Then we'll come to the crux of this lecture, that's about steady state errors, some equations, and then there's something called static error coefficients. I'll be talking about that. So if you know the error coefficients, you can find the errors. So that is why they are important. And then we'll study about static error coefficients for type 0 system. Once you know this, the remaining will be easy. Static error coefficient for type 1 systems, static error coefficients of type 2 systems. There's a typo here. Okay. So why all this is, by this time you would realize that the static error coefficients and steady state error depends on the type of the system. That is why type is important. You remember my example on periodic table. We classify elements as group 1, group 2, group 3. The most characteristic part is the number of electrons in the valence shell. Here we classify it based on the type of the system as far as errors are concerned. So that is why I am giving some importance for type. Then we'll summarize. Okay. So let me go to the interesting part of examples. So recall that a step response of a system has a transient part and a steady state part. The transient part would look like this. This part is called transient. Okay. So transient means where there is oscillation, and so this part is called the transient part. And you can see here that the response is settled. So if you consider the example of an ammeter, if you send a current of say 2.5 ampere, it will oscillate and then it will settle to 2.5 ampere. So we are in the transient part, we are interested whether how much is the oscillation, as we saw in the last class, what is the maximum overshoot, what is the rise time, when is the peak time. So all these are of interest. Okay. When does it settling time. So all these numbers are of interest in transient part. Suppose we have all these very great numbers. So maximum overshoot is less, rise time is less, settling time is less. Would you call this a good ammeter? Suppose the response is like this. So here it has settled very fast. This ammeter, this red graph I had drawn, it has settled very fast. Do you call this a good ammeter? No. Because when you send a 2.5 ampere current, what is it showing? When you send 2.5 ampere current, it is showing 2.2 amperes. So there is an error of there is an error of 0.3, which is not good. So we want, in control system, when you are designing control system, we want good transient performance and good steady state performance. This error, which I have marked here, this error is called the steady state error for a step input. That is, you suddenly apply a current of 2.5 ampere, it oscillates or may not oscillate and finally settle to some value. So this is not acceptable. Being engineers, if you send 2.5 ampere current and if it shows 2.4999, it's okay. It's okay for us. So we want steady state error to be within some good within good limits. So say if you are buying sugar, 1 kilogram sugar, if it is 1.005 kilogram, it is okay. So the steady state error for the weighing machine which is weighing sugar, if it is 5 grams, it is okay. But if you are buying gold and if there is a steady state error of 5 gram, either way it will be a problem. So steady state error depends on the value of the steady state error, has the importance based on the context. So the point is, if you are having a weighing machine to measure gold, weight of gold, the steady state error should be less than some 0.1 milligram or 0.01 milligram. If you are measuring current in an electronic circuit, the steady state error should be less than 0.001 milliampere. But if you are measuring current in a power system, the steady state error could be 0.1 ampere. So it depends, okay. So this is a ramp input. This dotted line, you can see the dotted line. You saw the dotted line. In the dotted line is the ramp input. You see the response. So this part is called the transient part, but there is an error here. So there is ramp input comes, you may want some system to follow some command, okay. So in that case, in some system there will be some steady state error. So it is an engineering issue. Depending upon the situation, you want to minimize steady state error. How much you want to minimize depends on your application. So this is another example where you could see the transient part of an RLC circuit. Here till here there's transients. Till around 0.008 second there is transients. After that there's a steady state. There is no steady state error here, okay. So I hope that is clear. I'll give you some non-trivial practical example. I debated with myself how much to talk about it. I will take 1 or 2 minutes. I hope this would be useful for many of you. So it is not only weighing machine or anything. There's an interesting problem in power system. Incidentally, I did my research in this area called load frequency control. So here what we want is we want the frequency of the power system to be 50 Hz. So if there is some sudden disturbance, the frequency will come down. So we have to do something so that the frequency will be back to 50 Hz. So we'll plot. So you can look here. This is something equivalent to frequency. Don't bother about this. So here, this is called change in frequency. So there was a step change. There was a sudden increase in load demand. Then what happened? In Idiki, we increased the power input. So what happened? Once you increase the power input, the frequency came down and there is no steady state error. So here, this part is called the transient. We want the transient to be good and we want the steady state error to be good. If you Google load frequency control and LGOD, you will get one interesting paper written in 1970, which is very readable, okay. I would recommend that you read it, okay. So when researchers do design controllers, they would design controllers so that the transient performance is good and steady state performance is good. Here we are demonstrating that with integral controller, Sometimes the performance will be okay, sometimes the performance will be not okay. I'll share one joke here. ചിലപ്പം ശരിയാവും ചിലപ്പം ശരിയാവില്ല. There's one WhatsApp video, a viral video. ചിലപ്പം ശരിയാവും ചിലപ്പം ശരിയാവില്ല. We don't want that in engineering. We want എപ്പോഴും ശരിയാകണം. So this when we change the parameters, what happens is with integral controller, the performance, the transient performance is horrible, okay? And steady state performance, it has not reached steady state. So people from 1972 onwards till 2020, people are doing a lot of research in this area, and you are studying a little bit in your power system classes under the heading load frequency control or area generation control. My point is, these things are used in practice, okay? People want an ammeter, a weighing machine, a power system, a rocket, an aircraft, everything should have good transient performance and good steady state performance. So I'll stop here. Rather, those who want to know more can send me a message. I'll be more than happy to explain to you. Those who are watching the video, they can put in the comment box. I will reply to you that also, okay? Those who are watching the video on YouTube, even not my students, my friends, if somebody is watching this, they can ask more doubt on this. One doctor asked me about the issue in power system when our Prime Minister asked all the loads to be switched on, I forgot the date, I think 8th August, 9 p.m. It was a big crisis for power system engineers. So they anticipated it, and they could get good transient and steady state performance. Okay, we'll go to a typical learning so that you all will get good marks. Very, very simple, Sida Sada class. Type number. Type of a system is equal to the number of poles at origin for the open loop transfer function. You have a system, you know already about systems, you know about closed loop transfer function, you know about open loop transfer function. So type of a system is decided by the number of poles at origin for the open loop transfer function. So we'll do a little exercise. The open loop transfer function of few systems are given below. Identify the open loop poles and the type number of the following systems. Write the same in the comment box or chat box, or you scribble it down on your book. So let me give you the transfer. This is very simple. So what is the question? You find the open loop poles. So this is the open loop transfer function. What are the open loop poles? Poles, as all of you know, is the value of S when the denominator becomes 0. So the denominator will become 0 when S is equal to 0, and S is equal to 0, there is one pole. S is equal to 0, there is one pole. 0 is very fancy. So at S equal to 0, there are 2 poles, and S equal to minus 2, there is 1 pole. Total, there are 3 poles. So this system is type 2 system. Why? Because there are 2 poles at origin. What about this system? 5 by S square by S plus 1 into S plus 2. I will pause for a while. You think, write it down. You have to identify the open loop poles and type of the system. So there are 4 open loop poles. S equal to 0, S equal to 0, again 2 poles at S equal to 0, then S equal to minus 1, S equal to minus 2. So there are 4 poles and 2 poles are at origin. So what is the type number? Type number is 2. So here find the type number and order of the system. So what is type number here? You find it out. What is type number here? Find it out. I'll tell you about the order. Order of the system is first order, because the maximum, the power of the differential equation behind this is called the order of the system. Or in this case, an easy way to find this, you find the power of S in the denominator. So the first term is a first order polynomial, second term is a second order polynomial, S square plus 3S plus 2. So I will give you the answer. The answer for this is, this system is type 0, first order. This system is type 0, second order. So this I will leave you as an exercise. Find the type and order of the system with the following open loop transfer functions. If you don't get the answer, please ask me, okay? I'll pause for a while for you to think and scribble down, or maybe when you're watching the video, you can pause it and write down the answer. Then only you proceed. Okay. If you don't know, if you can't do this, please ask me. Send me a message. I will answer it immediately. That is during the class time. I will be available online. So you send me in chat box if you have any doubt, or send me a WhatsApp message. I'll be happy to see the correct answers. Okay. So let us move. Steady state error and error transfer function. This is the closed loop transfer function. Many questions you will see about a system with open loop transfer, a unity feedback system. This system has a speciality. This system, the feedback is unity. You can see that in this path there is no gain. So these kind of systems are called unity feedback system. For our study, to make things simple, we will be more often than not considering unity feedback system. And GFS is called the open loop transfer function. Okay. So we know about open loop transfer function. We know the closed loop transfer function, CS by RS, we have seen earlier. It is GS by 1 plus GS HS. Here we want error transfer function. EFS is RFS minus BFS. You look here. This is EFS, which is equal to RFS minus BFS. Then what is BFS? The same signal CFS is coming here. CFS is coming here, so I can substitute BFS by CFS, RFS minus CFS. And what is CFS? You look here, what is CFS? It is GFS into EFS. So I have substituted GFS into EFS. So I took this GFS into EFS on the other side. So I'll get EFS plus GFS into EFS equal to RFS. So I can take EFS common. So EFS, if I take common, I'll get EFS by RFS as 1 by 1 plus GS. So this transfer function is called error transfer function. So what is error transfer function? EFS by RFS is equal to 1 by 1 plus GFS. So how will you find steady state error for any input? Step 1 is you know the input. So you find RFS. That is Laplace transform of the specified input. Step 2, find EFS. What is EFS? We know EFS by RFS is 1 by 1 plus GS. So EFS is 1 by 1 plus GS into RFS. Then you find what? The steady state error. This is why I said Laplace transform is very important. EFS, this part is very easy for all of you. Steady state error, I gave you practical example. It is the error as time tends to infinity. So we are measuring 2.5 ampere current. We look the error, how much it is different from 2.5 ampere, not at this time, as t tends to infinity. So according to final value theorem, limit t tending to infinity E of t is equal to limit s tending to 0 s EFS. So I don't want you to switch off your ears, okay? Don't mind, okay? This is a very important rule in Laplace transforms. So we can find the limit very, very easily. So I will stop this video here, and the remaining part I will talk it in the next part of the video. So thank you.